Welcome, everybody. We can get started with our 11:30 press conference. This one's on dynamic Mars from long-term observations. And this press conference coincides with the embargo lifted today on a paper that's in Nature Geoscience about the findings that the researchers will be speaking about. Our speakers, we have three speakers who will speak in this order. Alfred McEwen, he's principal investigator for the high-resolution imaging science experiment on the NASA Mars Reconnaissance Orbiter, and he's with the University of Arizona in Tucson. Colin Dundas is a science team member for high-resolution imaging science experiment on the Reconnaissance Orbiter. He's with the U.S. Geological Survey in Flagstaff, Arizona. And Robert Haberle is the co-investigator for Mars Color Imager on the NASA Mars Reconnaissance Orbiter. He's with NASA Ames Research Center in Moffett Field, California.
Okay, good morning, everyone. I'm happy to announce that Mars is alive and active in many ways, both the surface and the atmosphere, and we think including surface flows of water today, even in equatorial regions. So I'm going to start with a video just to review active Mars surface features, at least, and then we'll each talk about new results. But initially, this is a very quick tour of Mars and its activity. So I think we start at the polar regions, and this shows a polar pit in the south polar residual cap of carbon dioxide, dry ice. These are growing over time, not shrinking, repeats. And Bob Haberle will talk more about that. In the North Pole, we have these giant scarps with avalanches that occur every spring as soon as the sun first hits these steep slopes. There are hundreds of these active dust CO2 avalanches. We think that's what they're composed of, and blocks of ice also fall down. And these are active as we observe. This is a little sequence of 3 color images, about a second between each image. So this is just about the actual speed, if you can see it actually moving there. We also, the polar regions each winter are covered in CO2 frost that condenses out of the atmosphere. And when the springtime comes, it defrosts in very interesting ways, forming patterns. This just flips between 2 images showing some of the spots. Here's a sequence of some dunes defrosting. Here they are, frost-covered. Cracks form on the surface in the CO2. These lead to eruptions of dark material from pressure of CO2 gas that builds up and erupts. We get dark sand flows on the steep slopes. The wind blows the dark material. Eventually, it's completely defrosted. So this happens every year, both poles. The Martian spiders are one very distinctive feature that forms, especially in the south polar region, associated with these active processes. The dunes are active. Here you can see a little sequence where you can watch the ripples move along, and even the whole dune is moving by about a meter per year, per Mars year. Here's a close-up look at that, and you can see some of the avalanches on the steep slope as well. There are dust devils, including some really monstrous tall ones. Here's a video that JPL put together the other year, based on a high-res image, but animating the motion of this, both the rotational motion and its motion along the surface. These happen in particular times and places on Mars. Here's an example of 2 active processes. First, a new impact at the top, and that impact triggered this very large dust avalanche. So this is a dusty slope. And here's another example. The darkest streaks are the most recent avalanches, and then over decades, these fade as dust is deposited from the atmosphere. The gullies on Mars are active. This shows one example in Gossa Crater. They're especially active on sand dunes, but this is a non-sand dune location. The blue deposit you see there at the bottom, that's the fan. That's new material that was deposited. And here's a little quick blink movie showing new deposits on the fan. If you look closely, you can see lobes, new lobes of material, maybe a couple of meters thick, that were deposited. We're surprised to find that these dunes are active in the winter and the spring when there is CO2 frost in the ground. That seems to be driving the activity, the current activity. Here's another example showing dark material flowing down the channel in the springtime, and this is all frosted. So, and we haven't seen the topography change here, but this is another type of activity that occurs commonly. We have found hundreds of new impacts that have formed over the past decade or so. Some of these expose ice, and Colin Dundas will talk more about these ice exposed by impacts, clean ice. Now I'm going to talk about recurring slope LINEAE, a terrible name, but these are potentially water flows. They're dark streaks that form now in the dust-free areas of Mars. They form and grow incrementally down the slope. Steep slopes, rocky slopes, the warmest times of year, and then they fade when they're inactive and recur in multiple years. Here's another JPL animation, as if you're in a helicopter flying through this crater and watching these change over periods of weeks, so the helicopter is not on a tight schedule, I guess. So that we found these initially in the southern middle latitudes, and that made a certain amount of sense because we know there is shallow ground ice in the middle latitudes, as the new impacts help to illustrate, but also on steep equator-facing slopes. So these are places where that get quite warm. So it's like the intersection of this residual ground ice and warm areas. That seemed to make sense. More recently, we have found that these slope streaks are active in equatorial regions of Mars, which is a bit more puzzling. And I'll go here to the PowerPoint presentation here. And okay, so recurring slope LINEAE in equatorial regions of Mars. We have now seen many of these, particularly in Valles Marineris, which is the deep canyon whose length is that of the United States from coast to coast. Some of these are rather long, more than 1 kilometer in length. The picture here shows an arrow that marks some of these. They are quite similar to the mid-latitude RSL and how they behave. Steep rocky slopes, they grow incrementally, then fade. But what's unusual here in the Valles Marineris region, you don't get strong seasons, it's at the equator, but instead they're active on north-facing slopes when the sun is to the north, and then it switches to activity on the south-facing slope when the sun moves to the south. And so there's seasonality associated with what slope aspect you're on. Here is a global map showing first the global altimetry from the MOLA experiment on Mars Global Surveyor. Red and white are high, blue is low. And at the bottom is an albedo map from the TESS instrument and plots of the confirmed RSL sites. These are sites where we've seen the full yearly sequence. And we see lots of these in the southern mid-latitudes. A bunch of them in Valles Marineris and close to Valles Marineris in smaller canyons. There's one in the northern mid-latitudes that we found so far, although it's a bit unusual. They occur at many altitudes except the very highest altitudes. We haven't found them above 2 kilometers. And they strongly prefer the darkest, lowest albedo portions of the planet, which are the least dusty areas. Here's yet another animated GIF, and there are more of these on the HiRISE website. This is a spot in Juvente Chasm, and this shows the close relationship between the RSL and pristine gullies. These are equatorial gullies, and you can see that there's a good match in size between the RSL and the gullies, and so this could be what is forming these gullies today. So who cares? So what? Well, this has implications for future exploration of Mars, in a positive sense, because this gives us a focus of where to look for extant life. There's lots of other challenges besides water, but nevertheless, these are at least relatively promising sites to explore further. This also could affect future exploration in terms of something called special regions, where extra planetary protection is needed, extra safeguarding, sterilization before we send a lander or a rover to those spots, because we don't want to contaminate it with earthly microbes. Previously, the equatorial region was considered non-special. This may require some reconsideration of that. So I will turn it over here to Colin to talk about icy impacts.
All right, thanks, Alfred. Alfred was just talking about the most likely liquid water on the surface of Mars today, but most water on Mars is in the form of ice. Most of it's in the large polar ice caps and the polar layered deposits. But as you go towards lower latitudes, ice is not at the surface, but it's found in the ground, potentially within centimeters of the surface. And theory suggested that this ice should be present down to somewhere in the mid-latitudes between around 40 or 50 degrees north. And we found a new way to probe this a few years ago as we began detecting new impacts on the surface. With a record of images stretching back for several decades, it's possible to compare new and old images and detect impacts. And the way this is generally done is with the Mars Reconnaissance Orbiter context camera. Large dark spots are often found. And what these are is the blast pattern that you can see around a crater. You can see in this image here, there's a small crater surrounded by ice at the center, and then a larger dark pattern. And so several hundred of these have now been found, comparing images from this long record that we have. And some of them do excavate ground ice, and so we can use these to map out ice in the subsurface where it can't be seen on the surface. What you can see here is a map of the distribution of these new craters. The red points show new craters that didn't excavate ice, and the blue points show where the ice was seen. You can see also that these craters are mainly found in the light-toned areas of this map. This shows the albedo of Mars, and that's because that's where these dark blast patterns are most easily seen. It's not that craters preferentially form there, it's that they're most easily detected there. What you can also see is that as you go towards higher latitudes, from about 40 degrees latitude north and up, these impacts tend to expose ice. And there's a couple in the southern hemisphere as well at very high latitudes. We found now ice in some of these new craters as close to the equator as 39 degrees north. And so this lets us do a couple of things. The first interesting thing about this ice is that it appears to be quite clean. These craters stay icy as we look at them over and over again with images from HiRISE for months or even years. And the ice must be sublimating during that time. It gets warm in the summer, enough for the ice to sublimate. And so that suggests that this is relatively clean ice that's being excavated, not just ice filling in the spaces in the dirt. The other interesting thing about this is that the distribution of ice on Mars depends on the water vapor in the atmosphere. If there's more water vapor in the atmosphere, then ice will be deposited in the ground closer and closer to the equator. So mapping the distribution of these craters lets us understand how much water has been in the atmosphere of Mars near the surface over the timescale of centuries to thousands of years that it takes for the ice to adjust. And so using models of the theory of this, we can estimate what kind of water content is required to match the distribution of the craters that we see. And it turns out that the amount of water vapor that we estimate near the surface is, over this thousands of year time scale, is somewhat higher than we would guess from estimates of the current amount of water vapor in the atmosphere. That could mean that the current measurements of the water vapor have it concentrated very near the surface, at least some of it, or it could be that the average over thousands of years is somewhat higher than the present. So these craters are giving us a window and a linkage from current geomorphology and impacts to climate and its status over thousands of years. But we've also learned quite a bit about the recent Martian climate, and I'll hand it over to Bob Haberle to talk more about that.
All right, thank you, Colin. For the past 16 years, we've had 9 spacecraft at Mars. 5 of them are still operating. Some of these spacecraft were landers, some were rovers, and some were orbiters, but all of them were equipped with payloads that can address the climate system during the present day. And I've been asked to just briefly discuss the dynamic nature of that climate system, which I generally define in terms of the seasonal cycles of dust, water, and carbon dioxide. And these cycles are linked together through the general circulation, the global circulation patterns. And we know there are seasonal cycles because we can measure the amount of water, CO2, and dust in the atmosphere, and they vary globally with season. So that means the atmosphere is exchanging material with the surface. So atmosphere-surface interactions are very important to this process. So let me go to the next slide here and talk about the dust cycle. The dust cycle is actually the most complicated of the three cycles I mentioned. And it's complicated because we don't really completely understand how dust gets into the atmosphere. We do know, however, that there are a variety of different storms that lift that dust in the atmosphere. And you can see an example of each of these storms on this slide. They range in scale from very small scale systems, dust devils, as Al showed you earlier, to very large scale storms that can actually spread dust over the entire planet to altitudes in excess of 40 or 50 kilometers. These are the so-called global dust storms. So this long-term set of observations has allowed us to begin to characterize the nature of these storms. However, we don't really completely understand the mechanisms that lead to having different kinds of storms, and in particular the global scale dust storms. They don't seem to occur every year. For example, in the next slide, there are a couple of images here of two what are called regional storms at this point. The one on the left was taken by the Viking Orbiter 2 back in 1977, and you can see a very nice, well-defined sort of ribbon of dust. The dust is relatively confined at this time, but only a few days later, that dust storm became a global event and spread dust all over the planet. The storm that you see on the right was recently imaged by MRO just last year at this time. It too began as a regional storm of about the same scale as the one on the left, but it did not go global. So while we have learned a lot about the morphology and the structure and the variability of these dust storms, we really don't completely understand why some of them become global and others do not. Let me now turn to the water cycle. Again, we know that there's a water cycle because we can measure water vapor in the atmosphere, and it varies seasonally and latitudinally. And one of the major questions about the water cycle is, well, what are the sources and sinks for that water? And again, from this long-term set of observations, we now know that the major source for atmospheric water is water ice at the North Pole. It's something that we call the residual North Polar Cap. So every year CO2 condenses at the poles, but eventually sublimates away during spring and summer, and at the North Pole it reveals a water ice cap, which heats up and provides water to the atmosphere. The interesting thing is that the South Pole also has a residual cap, but it's not water, it's actually CO2, dry ice, and it survives all year long. And that cap will act as a sink for water. So we have a source at the North Pole and a sink at the South. In addition to those sources, we also have seasonal ice deposits, and we also have potentially water exchanging with the regolith. So we've learned a lot about sources and sinks. What we don't know today is whether these sources and sinks are gaining on a net annual basis or not. And this question is a very important question when you're interested in long-term climate change of the nature that Colin was describing. We would like to know how the ice that they're finding at these lower latitudes actually got there. And so by studying the present-day water cycle, we hope to be able to answer those questions in the future. And finally, let me turn to the CO2 cycle. I think everybody is familiar with the familiar waxing and waning of the polar caps on Mars. This is because it gets cold enough in the polar region for CO2, the main atmospheric constituent, to condense on the surface. So during the winter, the polar caps grow and they pull mass out of the atmosphere. And then the opposite occurs during spring and summer when the caps are sublimating. So the mass of the atmosphere is changing on a seasonal basis because of this cycle. And we can actually see that signature in pressure data. Pressure is a very good measure of the mass per unit area in a column of atmosphere. And what is shown in this slide here are pressure measurements from the Viking landers, which was taken in the 1970s, and then the more recent measurements from MSL during the past year. This period of time shown on this graph covers about 3/4 of a Martian year, beginning in northern summer, southern winter. So that's the minimum. The minimum in that curve here corresponds to when the south seasonal cap is at its maximum extent. And then as the season progresses, the cap retreats and puts mass back into the atmosphere, and you can see the pressures rise. What we're hoping to learn from this pressure data are many things about the atmosphere today, but we're also interested in potential climate change. If I can have the next slide. As Al mentioned in his talk, there are these pits that are changing in morphology in the south residual cap, and there are other observations that show scarps retreating, and there has been a suggestion that the south polar residual cap may actually be disappearing steadily year after year. If that is the case, and if the disappearing mass is going into the atmosphere, we should see a signal of that in the pressure data. So here's another really good point about the value of long-term measurements, because we had pressure measurements during Viking, and now we have pressure measurements during MSL, a period of about 19 Mars years. We can begin to assess the potential that the south polar cap is actually disappearing. So in conclusion, I think there's a real value in having long-term measurements, and we're looking very much forward to continued measurements to help us characterize and understand the dynamic nature of the Martian climate system.
Okay, we'll open up for questions now. Are there any questions from the floor?
Hi, Irene Klotz with Discovery Channel and Reuters. How far beneath the surface do you think the ice is at that 39-degree inclination as exposed by the impact craters?
It should be within tens of centimeters, a meter or so at most. These craters that are excavating it are the largest is over 20 meters in diameter, but that's at high latitude, so these don't dig down all that far. It's generally close to the surface.
Thanks. And is there any data from any of the orbiters as to the contents of that ice?
It's water ice, and what's somewhat surprising is that because it stays relatively bright so long, it seems to be relatively clean, relatively pure water ice.
Other questions? Any questions from the chat?
Camille Carlisle with Sky and Telescope. Why would the RSLs prefer the least dusty locations? And also, how much does the atmospheric pressure on Earth change seasonally compared with the seasonal changes on Mars?
Okay, well, we observe the RSL in the least dusty regions. One reason is that they clearly favor the warmest places, times and places, and the darker the albedo, the more of the sun's heat it absorbs. That's one reason. There's also possibly other reasons, such as if you have fine dust, that's like an insulating layer, and so the heat stays right at the surface. If you have rocky material, that conducts the heat deeper into the subsurface, although still not very deep. So if subsurface ices need to be warmed to create RSL activity, then these are the sites where the sun's heat is both intense and gets conducted deeper into the shallow subsurface. As far as atmospheric pressure compared to Earth, I think Bob can answer that.
Well, yeah, I think the main difference is that on Earth, the major atmospheric constituents do not condense. The major constituents are nitrogen and oxygen. The only thing that condenses in the Earth's atmosphere is water vapor, and that's a very minor component of the total composition of the Earth's atmosphere. The situation on Mars is much different because the main constituent, carbon dioxide, condenses.
Harvey Lyford, freelance. Professor McEwen, your opening remark was quite dramatic, and I guess it was meant to be. My question is, how much of that was new or surprising of Mars being alive and well, and however you phrased it, and how much is just learning new details about processes we already knew?
Okay, great question. We've known about dust blowing around on the surface of Mars for many decades, even observed from Earth. And we've known about the polar caps growing and shrinking, even from telescopic observations. And we got higher resolution observations of that from spacecraft. I think HiRISE and also the Mars Observer Camera are revolutionary in that now we're getting down to the spatial resolution where we can see topographic changes. And this has allowed us to really see different classes of changes. And for example, the sand dunes, there were lots of debates about whether or not they were active. It was only with HiRISE data in recent years, and Nathan Bridges is sitting here, you can ask him more, that we've really seen these things move and active. We know for sure many of them are definitely active today. That's new. We saw evidence for these very fresh, pristine-looking gullies, but were they changing today? And what time of year were they changing? So this was, we saw some changes from Mars Global Surveyor MACH, but we didn't know what time of year those occurred. With MRO, it's a more flexible spacecraft that can point to the side. We can target sites of interest more frequently. We've been able to nail that down, and we were surprised to see that happening in the winter and early spring associated with CO2 frost, and most workers had thought that liquid water was involved in forming those gullies, and it wasn't even clear that they were forming today or not. So that's new. That we started seeing new impact craters from MACH again. We've seen many more from Mars Global Surveyor, and the ice is new. And then the RSL are completely new, and this to me is the biggest surprise from the HiRISE experiment. After seeing the gullies form associated with CO2, I was coming to the conclusion, okay, that's where the action is. The CO2 frost drives activity, the wind drives activity, no water. But then these RSL are very different. They're totally anti-correlated in season with these other activities. It's definitely a different class of activity. The temperatures are consistent with the presence and activity of liquid water. So that to me was the biggest surprise of HiRISE so far. There's new details about the atmosphere as well. Not sure that I'm the best to point that out, but hopefully that answered your question. The avalanches are new as well.
Norm Sperling, I remember an orbiter picture from Viking showing what looked like giant icicles hanging down on the edge of the retreating polar ice cap. Those, I should think, would make wonderful animations, and I haven't seen a thing about it since 1977.
Okay, I don't know, I can't visualize what you're looking at. Viking orbiters observed at fairly low resolution, so they wouldn't have been able to resolve icicles unless they were, you know, huge, really huge icicles. So I think this was observing some of the albedo or brightness changes, and the frost changes at the edge of the polar cap. I'm not sure, but we have been observing that in much greater detail and understanding how this changes with the season and also from year to year, and there seems to be a close connection to the dust storms, whether there's a dusty air or not. We do have some animations of that, and you're right, they're quite interesting.
Emily Lochtawala with the Planetary Society. I'm wondering if you've actually detected a change in the density of the atmosphere as more CO2 is coming into it from the South Polar Cap. And I'm also wondering if there were climate change happening on Mars, what would be the, what kinds of things could be driving secular change in the climate on Mars?
Well, it's a little too early to tell whether we are actually seeing a signal for secular climate change. There is a hint of it when you take a look at the Phoenix data and compare that with Viking data. But the Phoenix data were fairly limited in time. It was a short-lived mission. When you look at the MSL data, the results are a little bit more ambiguous, and I think what we need to do is wait for a longer record of measurements from MSL and do a little bit more of a careful analysis on that data. But I do think the sensors have the accuracy and the precision to actually detect the signal if it's there. I'm not sure it's there. If it is there and the cap is losing mass, then it does suggest some sort of climate change is going on. What's driving that is unclear at the time. I mean, to first order, you would think that things are getting warmer a little bit, but we don't see any real evidence for that. So the mechanism for actually causing the cap to lose mass, if it is losing mass, is unclear at this time.
We can also observe the South Polar Cap, and we very easily see these pits growing, but what we don't know very well is the vertical dimension. Is the CO2 condensing elsewhere? But we're attempting to measure that with high-resolution topographic data, and the longer time base we have, the easier it is to measure changes.
Any other questions? Any more questions from the chat?
I think we have one, but you may have just kind of answered it. Why the solar do you have any thoughts on why the South Polar Cap might be disappearing over the long term? But I think you just...
Yeah, Bob addressed that. One theory is that it's actually cyclical, so it disappears and regrows. Another is that it could be related to dust activity, where dust changes the reflectivity of the surface, and then the surface absorbs more or less sunlight as a result of that dust. It's not burning coal that's doing it on Mars.
Any other questions from working press?
I think I saw Jim Green raise his hand.
Okay, well, thank you very much. That ends this press conference. Thank you for your presentations and everyone else for participating. And we'll have our next press conference at 1:30. That's going to be on the Battle of Fire and Ice, new scientific results from Comet ISON.